In this video, we're going to talk about dual. And no, I'm not talking about two people shooting each other with pistols. I'm talking about the diffusing update algorithm, which is the fundamental algorithm that powers Eigrp, that helps Eigrp to look at routes that are learned, to determine if they're actually usable or not, to determine which route is the best, and some of the terminology that goes behind the diffusing update algorithm. So let's get into some of the terms first of all. The successor. So once again, the example of I'm a router, you're a router, and we are connected via Eigrp. If I advertise some network to you, let's say the 90 network, and you are using me to get to the 90 network, I am the best route that you have, I would be considered your successor for that route. So I'm the successor is the router that you use as your next hop. Now, if somebody else advertises the 90 network to you and our paths are both the same, and you say, okay, there's nothing different here, I'm going to put both of them into the routing table, then you have two successors. So you could have more than one successor. The successor is whatever neighbor you're using to put into the routing table, the best route that you're using, the best neighbor that you're using to get to a particular prefix. Now, let's say that I advertise the 90.90 network to you with an Eigrp distance of 1,000. And all of a sudden, here comes in another neighbor of yours who advertises that exact same network, but with a distance of 500. He's better than me. So you would now use him. His route would be the one and only route in your routing table. He would be considered your successor. My route that I gave you to that same network, well, you wouldn't put that in your routing table, but you would store it. Eigrp has a totally different table called a topology table, where it stores all the routes it learns from any given neighbor. So the topology table stores everything, and then those routes might make it into the routing table based on factors like administrative distance and things like that. So in that particular case, his route, which was a distance of 500, he will be your successor for that route. My route, which you're storing as sort of like a backup route, well, I would be considered a feasible successor for that route. So a feasible successor is, like it says, it's feasible. This guy could possibly be my successor if my successor goes away, or if my successor informs me that he can no longer get to that route. Then I could use my feasible successor. So two very important terms that you know, successor and feasible successor. All right, now some other terminology, and this is going to be with regards to distance. Remember, distance is the name of the Eigrp metric, and distance is a big number that comes as a result of that big nasty formula that we saw. 256 times all these values equals Eigrp distance. So the first one we need to know is something called the feasible distance. So in that exact same scenario where I am your feasible successor, I'm not quite as good as that guy. He's the one you're using. He is your successor to get to the 90.90 network. So whatever your distance is to go through him all the way to the destination, that is your feasible distance. Now remember, that's based on a result of all of the delays, the sum of the delays going all the way to you, plus the minimum bandwidth along the path times 256. So whatever that big number is, that is your feasible distance. Now, when I advertise a route to you, so let's say there's some route behind me and I advertise that to you in an Eigrp update. When I send you my advertisement, all I tell you is what I think it costs me to get to that route. In other words, I don't factor the bandwidth of this link into my equation. I don't factor the delay of this link between you and me into this equation because I don't go this way to get to that route. I go this way. So I take a look at the sum of my delays. I take a look at, from my perspective, the lowest bandwidth along the path. And then from that, I compute my feasible distance to get to that network. Well, when I send you an Eigrp update, I don't actually tell you what my distance is. You know what I tell you? I tell you what I used to come up with my distance. So for example, whatever I think the lowest bandwidth is, that's what I tell you. Whatever I think the sum of the delays is for me, that's what I tell you. Whatever I think the load and reliability are, even though I'm not using them, that's what I tell you. So I'm reporting to you, I am advertising to you what I used to come up with my own feasible distance. So those values that I'm sending to you is called the reported distance. That's also sometimes called the advertised distance. Exactly the same thing. Reported distance, advertised distance is what my neighbor thinks it costs to get to that route. From my neighbor's perspective, what's his lowest bandwidth? What's his sum of his delays? And then I can take all that stuff, put it into a formula, and I can figure out what distance he's using. But then you have to factor in, okay, what about that link between me and my neighbor? That's what's going to be your total distance. Now, in the case of most routing protocols, they have mechanisms built in to try to detect and prevent routing loops from happening. What is a routing loop, you say? Well, a routing loop is a situation where something gets messed up in a routing table somewhere, and instead of a route actually pointing in the correct direction towards where the destination is, it points in the wrong direction. And so what ends up happening is when packets enter the network, instead of going to the destination, they end up circling in the network because it's somewhere around the way we've got two routers pointing in the wrong way. And so the packets just keep circling back and forth. That's called a routing loop. So Eigrp has a formula or a logic that it uses to try to detect if an incoming update could potentially be a routing loop. So how does it do that? Well, let's take a look at this real simple premise. So let's say I have a router right here, and he knows that he's got two neighbors. So we'll say this is router 1, router 2, router 3, and here's his neighbor over here, router X. Okay, so router X sends him some route, let's say for the 3 network. Now, up until now, this is the only time router 1 has ever heard of the 3 network. So he puts in his Eigrp topology table an entry for that. He says, okay, I've just learned about the 3 network via router X. And he says, when I compute my total distance, my feasible distance, which is the best distance I have, is let's say 1,000. That's my feasible distance. Now at this point, router 1 advertises that route to router 2. He's going to advertise it to router 3 as well, but for now, let's just say that we're looking at this snapshot in time just after he sent the routing update to router 2. Well, what do we know? We know that when he sends out that routing update for the 3 network, he's telling router 2, here's the bandwidth I used, here's the sum of the delays I used to come up with my feasible distance of 1,000. So in this particular case, we're now saying this is the reported distance. Sorry, that looks really messy. Let me clean that up a little bit here for us. Okay, so his reported distance is equal to 1,000. Now we know that in reality he's not actually saying 1,000, he's saying here are the numbers that I used to come up with 1,000. Now how do we prevent routing loops? Well, we know something. If this routing update were somehow to circle back around and come back in this way, what do we know? We know that whatever the reported distance would be, if this was the same route I had sent out this way and coming back to me, we know it would be at least equal to 1,000 or greater, right? So if this is my own route being reflected back to me, the reported distance would have to be the same as 1,000 or possibly larger than 1,000. There's no way this route could come back to me with a reported distance of less than 1,000 if it was my own route coming back to me. So this is something called the feasibility condition. Eigrp says, okay, once I learn of a route the first time, well, there's no way for me to tell if there's a loop. If I only have one entry for this, there's nothing to compare it against, I'll put it in my routing table. But if somebody else advertises that exact same route to me, so now I've learned about the same route twice or 3 times, then I'm going to perform what's called the feasibility condition, which means I'm going to take a look at their reported distance and I'm going to compare it against my feasible distance. If their reported distance is the same number as this or larger, that is suspect. That could possibly be my own route coming right back to me. I don't think I want to use that because that might be leading to a routing loop. So in that particular situation, we would say that that route did not meet the feasibility condition. It's not feasible. We cannot even consider it because it could be a potential routing loop. And so that's what we see right here. How do we calculate the feasible successor? In other words, if somebody reports in a route to us, how do we even say, is this potentially a better path? Is this potentially maybe not a better path, but something I could use as a backup that could feasibly be my successor? And so we have to run it through the feasibility condition, which means if the reported distance is less than my current feasible distance, we're good. It's not a loop. There's no way it could be a loop. But if the reported distance from my neighbor for this route I already have is equal to or greater than my feasible distance, that could potentially be a loop, and I'm not going to use it. Let's do an example of this. So I'm going to configure Eigrp on these three routers right here. That guy, and that guy. And I'm going to form neighbor relationships this way. Okay. I'm not going to have switch 2 and router 3 become Eigrp neighbors. I'm just going to have switch 2 and router 3 become Eigrp neighbors with switch 3 with the sole intention of having them advertise this network. Okay. So what we should see at the very beginning is that switch 3 learns about the 323 network and he should have two successors, right? Two equal cost paths. The path to that network via switch 2 should be just as good as a path via router 3. So let's do that to begin with. So you may want to pause this video and take a snapshot of this picture real quick with some image capture software or something so you can follow along and you can keep track of where I am as I configure this stuff. All right. Okay, so let's start with switch 3. And here we're going to see our first Eigrp commands. At the global configuration level, you just type router, Eigrp, and then you have to put your autonomous system number. Now, like I said, it can be any number you want as long as it's the same on all the routers. So I'm just going to use autonomous system 100. I'm just used to using that in my labs all the time. Now, just like RIP, I have to use the network statement. So I take a look at my topology diagram and I say, well, I want switch 3 to activate it on the 232 network. That'll have him start speaking this. And I want him to activate it on the 333 network. That'll have him start speaking on here. Now with Eigrp, you have two options with the network statement. Two ways that you could type it in. I could just type in the classful network, like 2000, and then hit enter. And then switch 3 would look around, and any interface he has that has an IP address beginning with the number 2, he would start speaking Eigrp on that. Or alternatively, I could actually enter the specific subnet that I want, network 2320. Now, if I just hit enter right now, if I just hit my return key on my keyboard, it will actually shorten that down. It will condense it down to 2000. So if I actually want to keep this format as it is, I have to put in a wildcard mask. And hopefully you've learned about wildcard masks when you learned about access lists at the ICMD1 level. So that's what I'm going to do. On switch 3, I'm going to activate Eigrp on just these two interfaces by specifying these specific networks and including wildcard masks so it keeps those networks just like it is. And I'm going to do that on switch 2 and router 3 as well. So here we go. I'm going to type network 2.3.2.0 and then the appropriate wildcard mask, and then network 3.3.3.0 and the appropriate wildcard mask. And I'm also going to type this command no auto-summary. In a lot of the newer Cisco iOS, this is actually the default command. which means don't automatically summarize things. If I want to do summarization of networks, I want to have control over it. I want to use specific commands so I can control what gets summarized and what doesn't. So that's what no auto summary says, do not summarize. Some of the older versions of Cisco iOS, like in 12.3 and 12.4, it actually defaulted to auto summary. And because I've been dealing with Eigrp for literally decades, I'm just sort of used to typing no auto-summary. Even though it's probably the default already and I don't have to type it anymore, I'm just used to typing it. Okay, so for switch 3, that's all I got to do. Just type router Eigrp, the autonomous system, and then the network statements that cover the interfaces where I want him to speak. So let's now go over to switch 2. So right now, even though I don't see it, switch 3 is currently sending out Eigrp hello packets every couple of seconds to that 224.0010 address. He's sending them out. I think it's like every 5 or 10 seconds that he's sending those out. Okay, so enable conft router Eigrp 100 network 2.3.2.0 000.255. Now what you're going to see is as soon as I hit the enter key here, within seconds, this guy is going to exchange hello packets with switch 3, and they're going to form an Eigrp neighborship. 1001, 1002, there you go. 2 seconds, and they saw each other, and they formed a neighbor relationship. All right, now I'm going to go ahead and activate Eigrp on the lower section. Okay, so what I just did right there is I told switch 2, not only do I want you running Eigrp here, but I just did a network statement for this, which now activated Eigrp on this segment. Now, I did that because without that network statement, he would not have permission to advertise this directly connected network. Like right now, switch 2 is not going to tell switch 3 about the 222 network because I have not included that in a network statement. But I did want him to tell him about the 323 network. However, I mentioned at the very beginning of this lab, I said I don't want switch 2 and router 3 forming an Eigrp neighborship. I want to include this network, but I don't want them talking to each other. So do you remember what I can do in switch 2 to say, hey, it's okay to advertise that network, but don't send any Eigrp hellos out fast Ethernet 0/3. That was the passive-interface command. Passive interface for fast Ethernet 0/3. Passive-interface fast Ethernet 0/3. So that will now prevent any kind of neighborship from forming between switch 2 and router 3. So let's just finish this up now with router 3. So I'll include a network statement that he shares with switch 3, and we'll see a neighborship form almost instantly from that. There we go. And then I will also include a network statement for that link that's shared between router 3 and switch 2. I do not have to put a passive interface command into this guy. I only have to do it on one side of the link. It wouldn't hurt to do it here, but since I already did it in switch 2, there's no way switch 2 and router 3 can ever become friends. There's no way they can become neighbors. Okay, so now what we should see is if I go over here to switch 3, he should have learned about the 323 network from both switch 2 and router 3. Let's take a look. See, that was switch 3. Show IP route. Let's just look at our routing table first. And you know what? I only want to look at Eigrp routes. So you can do that. You can do show IP route and then type in the type of routes you want to see. You can do show IP route static, show IP route connected. In this case, I only want to see Eigrp routes. And sure enough, he's learned about the 323 network from both of these guys. And notice they were both advertised as Eigrp internal routes, and I know that because the administrative distance is 90. And here is my feasible distance. This is the result of that big, massive formula, and we can see they're both exactly the same. So one also thing you need to know as far as the CCNA is concerned is you need to know how to look at and interpret the Eigrp topology table. And that's just show IP Eigrp topology. So when you see a capital P, that means an entry is passive. That's good. That means this entry is usable. I can forward packets to it. So right here we see 323 and it says 2 successors. Both routers are equally the same. Now, next thing I'm going to do, oh, and by the way, as you can see here, this is the reported distance. So each one of those other devices, when they calculate their distance, this is what their distance is to that directly connected segment that they share. But then when I factored in my own bandwidth and delay to get to them, it bumped up my distance a little bit. So my feasible distance, which is my best distance to this network, is 30,720. Now the next thing I'm going to do is I'm going to say, okay, well, I want switch 2 to be my successor, and I want router 3 to be a feasible successor. In other words, I don't want him to be quite as good as switch 2. What can I do about that? Well, there's a couple of things. I could make some changes to this interface right here, make that interface look worse than it really is, maybe lower the bandwidth, increase the delay, or I could make some changes to this interface right here and lower the bandwidth or increase the delay. I think what I'm going to do is I'm going to go on to router 3 and I'm going to go onto this interface, and using the delay command, I'm going to make the delay look horrible. I'm going to make the delay look like it just takes so long to put bits on that wire. And so that will cause router 3 to modify his reported distance. His reported distance will get bigger. It will get less preferable. And so then switch 3 should say, oh, you guys aren't the same anymore. All right, so now I'm going to have switch 2 by my successor. And router 3, I'll keep you in my topology table, but you're going to be a feasible successor. So let's do that. On router 3, let's change fast Ethernet 00. Interface fast Ethernet 0/0. And I'll say delay. And let's say the delay is, I don't know, let's say something really big. What was that maximum number there? 116,770,000. Why don't we do 1 million? 1, 2, 3, 1, 2, 3. Delay 1 million. Okay, now let's go back to switch 3 and let's take a look at his Eigrp topology table. Now look at this. 1 successor. Well, what happened to router 3? I mean, he still has that neighbor, right? How do you check? How do you check to see if I still have that router as a neighbor? Here's another command you want to know. Show IP Eigrp neighbor. Show IP Eigrp neighbor. And sure enough, here is the router 3, and here is switch 2. If he wasn't a neighbor, he would not show up in this output. So where's the route from switch 2? The reality is I made that delay so horrible that when switch 2 advertised it, this device said, well, take a look at this. Show IP Eigrp all dash links. So look at this. Here is, this is router 3. Yes, this is router 3. Okay. 2, 3, 2, 3, 2, 3. Something got changed here. Okay, so it changed. So here is what we're looking at. So for the 323 network, it now says I have 1 successor. So I've only got 1 best path. And your successors are always at the top of the list. So this first guy right here, that is my successor. And you can see that because my feasible distance, my best distance, matches this. So that's my successor. Now, why didn't this guy right here show up? When I did show IP Eigrp topology, so notice the difference here. When I do this command without the keyword all dash links, contrast the output. Here, with the all links keyword, I see both guys who advertise the route. Here, without the all links keyword, I only see my successor. Why don't I see this guy? Because when you type the command show IP Eigrp topology, it will only show you your successors and your feasible successors. Now you might be thinking, wait a second, Keith, I mean, isn't this guy a feasible successor? No, he's not, because he did not meet the feasibility condition. Look what he did. When this guy advertised 323, he said, my reported distance is this horrible number, 256 million and something or other. And remember, what does the feasibility condition says? It says, okay, if I've already got this route in my table, if anybody ever advertises that same route to me, their reported distance better be less than this. It better be less than 30,720, because if it is the same or greater than this, that could be my own route circling right back to me again. That could be a loop. It says, wow, that is definitely not less than 30,720. You did not meet the feasibility condition. So therefore, you are not considered as a feasible successor. What's interesting is he still keeps it in there. It's still in his memory. He's just not even considered as a backup route right now. So I made the delay too horrible. I made the delay so horrible that the reported distance did not meet the feasibility condition.